Hello and welcome to algorithms. In this video we are going to look at what an algorithm is and then have a look at some examples. The predominant focus of this playlist on my channel is to focus on modelling with algorithms, which is a further mathematics option for A-level mathematics on the OCR MEI specification. Okay. Modelling with algorithms, and in modelling with algorithms, this optional module, we look at graphs and graph theory, we look at networks and network problems, we look at critical path analysis, we look at network flows, we look at how to solve linear program problems graphically, we look at how to solve linear programming problems using simplex methods, and then we also look at some network problems that we would have seen earlier. And how we can reformulate those as linear programs as well. Plus there's little bits of technology kicking around, outputs from online solvers, spreadsheet solvers for linear programming as well. So we'll see all of this throughout this playlist of videos. Okay, so algorithms. I'm just going to start very basic. What is an algorithm? An algorithm is a set of instructions. I can't spell. There we go. Instructions. Specifically, actually, a finite set of instructions. If it doesn't have an end, or if it's stuck in a loop, it is not classed as an algorithm. It's got to have a finite set of instructions, and it's important to distinguish between kind of rules and instructions. An algorithm will have the same result no matter who carries it out, whereas rules and ideas where you make choices within a process is not classed as an algorithm because it can look slightly different every time you do it, or if someone else does it, it looks slightly different. Algorithms have a very strict definition. No matter who does it, who carries out the algorithm, the output will be the same. Okay. Nice, clear instructions. So here are some nice, clear instructions. We've got 4 steps. Steps 1, 2, 3, and 4. All laid out nice and clearly, and we're going to apply a pair of numbers to this algorithm, and then we're going to apply a second pair of numbers to this algorithm. I'm going to try and see perhaps what this algorithm might be doing. Okay, so for part A of this question, we are going to apply this algorithm, steps 1 to 4, to the numbers 5 and 16. I'm going to put 5 on the left and 16 on the right. Step 1, write 2 numbers side by side in the same row. Okay, so I'm going to put 5 and 16. Okay, so they are side by side in the same row following the instructions that are given. Step 2, beneath the left number, write double that number, and beneath the right number, write half of that number, rounding down. Okay, so the left-hand number, I'm going to write twice that number, so that's going to be the number 10. And under the right-hand number, I'm going to write half of it, rounding down, which is the number 8. Okay, that's step 2. Step 3, repeat step 2 until the right number is 1. Okay, so I'm going to keep doubling the left-hand number and keep halving the right-hand number until I get to 1 in the right-hand number. So it's going to be 20, and then 4, 40, and then 2, and then 80, and then 1. I'm going to stop. Step 4. Delete the rows where the right number is even, add up the remaining left numbers, and this is the result. Okay, so delete them where the right number is even. So that's going to go, that's going to go, that's going to go, and that's going to go. That leaves me with this one. So the answer is 80. Okay, so when I put 5 and 16 into this algorithm, the output is 80. Have a guess at what this algorithm might be doing. If you can't, don't worry, we will go through that a bit later. Let's have a go at this one here. So we've got 12 and 23. So I'm going to apply this algorithm again, but this time to these 2 numbers. I'm going to put 12 on the left and 23 on the right. So 12 goes on the left, 23 goes on the right. That's step number 1. Step 2, beneath the left number, write double that number. Beneath the right number, write half of that number, rounding down. I'm going to repeat that until the right-hand number is the number 1. So that's going to be the number 24. I'm going to double it. Half it, or half of that is 11.5, but it says rounding down, so I'm going to put 11 in there. Double that, so that's 48. And then again, I'm going to half that, but round down, so that's number 5. And then double that, I'm going to get 96, and then half that, that's going to be the number 2. Okay, again, rounding down. And then this one's going to be 192, and then that's going to be the number 1. Okay. And then finally, step 4, delete the rows where the right number is even and add up the remaining left numbers. So I'm just going to delete that row, and then I'm going to add up the remaining numbers here. So that's going to be 240, 264, 276, and that is the result, 276. What is this algorithm doing? Well, if you guessed that they are multiplying the numbers together, then you would be correct. Okay, this algorithm is a way to multiply two numbers together. So 5 and 16 went in for part A, and the output was 80. 5 times 16 is 80. And then 12 and 23 went in on the second part of the question, and output was 276. Okay, second question. Okay, quite a different one. This time we're given a definition of f of x squared minus 5. We defined L as being 2 and R as being 3. And what we're going to do is we're going to follow the set of instructions until we come to a stop. Okay, we'll try and work out what this algorithm is doing. So compute M, which is a half L plus R. So M is going to be the midpoint of L and R. So in this case, it's going to be, going to input 2 and 3. So the M is going to be 2.5, which is the midpoint. Then we're going to compute f of m. Oh, I've not got a space for f of m. Let's change that to f of m. And then I'm going to pop print over on this side. There we go. So compute f of m. This time I'm going to get the calculator out. Okay, right. So 2.5 squared minus 5. That is 1.25. If f of m is less than 0, it is not. So ignore that bit. Otherwise, change the value of r to m. So r is now going to be what m was. So that is now 2.5. Repeat steps 1 to 3 until r minus l is less than 0.2. Okay, so we're going to go back to step 1, and we're going to compute this again. And the rule is, when you've got these tables of variables, as you progress through them, always run from left to right and then down. So if I now I'm told to replace the letter L, I'm going to go to the next row down, because if I go here, I'm going backwards to the left. It's much better just to follow this table down so that it's clear what your variables are doing. Okay, so we're going to compute M, which is the midpoint of L and R. L is 2, that's not been updated, so it's still 2, and R is 2.5. So M is 2.25, okay, the midpoint of those two. So I'm going to plug that in, 2.25 squared minus 5, and that is 0.065. Okay. Less than 0, it's not, it's bigger than 0. So we don't change L to M, we're going to change the value of R to M. So this is now 2.25. Repeat steps 1 to 3 until R minus L is less than 0.2. That's not 0.2, so we're going to repeat again. So midpoint is 2.125. Compute f of m. So it's 2.125 squared minus 5. That is minus 0.484375. If f of m is less than 0, change the value of L to m. It is less than 0, so I'm going to change the value of L to 2. Repeat steps 1 to 3 until R minus L, that should be 1.25. R minus L is less than 0.2. It is now less than 0.2 because it's 0.125, difference between them. So we're going to move on to step 5 now, which is print M. So I'm going to print, and M is 2.125. Okay. And that's the algorithm, that's the output of the algorithm. When it says print something, that tends to mean that is the output. So 2.125 is the output to this algorithm. What is this algorithm doing? Well, it's using a bisection search to solve this equation is equal to 0, this f of x equals 0 is that equation. Is it trying to solve? Essentially, it's trying to find the square root of 5. If we wanted it to be a bit more accurate, okay, the square root of 5 is not really that close to that number. It is 0.236, okay, so it's still a fair distance away, then we could decrease this value here, and then that would give you do more iterations of this process to get a better approximation of the root. Okay, so that was that one. And then a final example is what's called a flow diagram or a flow chart. So in this question, int x is the integer part of x. So for example, int 5.7 is 5. So just ignore anything after the decimal point and it just becomes the integer. For a flow chart or flow diagram, we have a start and an end. Okay, end is down here. Any instructions are given in rectangular boxes, and any questions are given in diamond-shaped boxes, which will have multiple outputs, and then you choose depending on what the situation is. So if R2 is bigger than 0, then we'd go here and then go back round again. If R2 is not bigger than 0, then we go down and then print R1 and stop. Okay. All right, so we're going to run this algorithm with A is 24 and B is 16. So it's the same kind of process as the first algorithm we did. Step 1, step 2, step 3, repeat step 3 until blah, 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 blah. It's just laid out as a flowchart. Okay. All right, so A is 24, B is 16, and notice there's another table here. So we are going to lay it out in this table form. Okay, input positive integers A and B. So we're told which two in the question to use this time. Let Q equal the integer part of B divided by A. So if I do B divided by A, that's 16 divided by 24. The integer part is, well, 0. R1 is B minus A times Q. So B is 16 and A times Q is going to be 0. So R1 is going to be 16. Okay, so that completes that box. We then move down the arrow into the next box. Let B equal A. So now move on to the next line. B is now 24. Let A equal R1. I'm not going to go backwards, I'm going to go all the way around. So A is going to equal R1. R1 is 16. So A is going to be 16. Q is the integer part of B divided by A. So 24 divided by 16 is 1. So if I do 24 divided by 16, that's 1.5, but integer part is just the 1. And then R2 is B minus A times Q. So it's going to be 24 minus 16. It's going to leave me with 8. Okay. Is R2 bigger than 0? Yes. R2 is 8. So it is. So we're going to go this way. Let R1 equal R2. Okay. So R1 is now going to be equal to R2. So you set that to be 8. Follow this round. And now we're back here again. Let B equal A. So follow the line round. B is now going to be A. So B is 16. Let A equal R1. Follow that one round. That's going to be here. So A is going to be 8. This is what R1 is. Q is the integer part of B divided by A. So 16 divided by 8 is 2, exactly 2. So that's going to be a 2 in there. And R2 is 16 minus 8 times 2, which is 0. So that goes in there. So that completes that box. Then we move on to this question. Is R2 bigger than 0? No, R2 is 0. So I'm going to carry on down here. Print R1 and stop. So R1 is going to be equal to 8, and then we're going to stop. Okay, that's the output from this algorithm. R1 equals 8, and I wonder if you can work out what it does. Have a guess. If you said it finds the highest common factor, then you'd be right. It does. You can put in any two positive integers A and B, and it will kick out the highest common factor. In this case, the highest common factor of 24 and 16 is the number 8. Okay, 8 is the biggest number that goes into both of those. All right, thank you very much for watching. We've got lots of videos to come on modelling with algorithms, so do check them out, and I hope you enjoy this course. Thank you very much for watching.